So let's take a look at Chapter 6, Standard Errors. And when we're talking about standard errors, we're talking about the standard area of the mean, a sampling distribution, or calculating a probability. So we're looking at a couple different types of errors here. So the first error can occur as early as the sampling stage for a study. So whenever a sample needs to be taken from a population, it's possible that you could get a sample that has different characteristics because we're not able to get all information about all people. So the difference that could be seen between the mean of a sample and the mean of a population is caused by the process when we use a random sampling process and we still get very significantly different values. We have to consider, could something in our sampling process have caused that? It's definitely not always, but it's something we always want to just kind of be aware of, as if we're really seeing a big difference, that it could be something in our sampling process and not necessarily in our calculations. So to help us really get a sense of how well a sample represents a population, we have identified this statistic called a standard error. So that's going to help us get to a number that explains things for us. So the standard error is the average amount of difference between the sample and the population. So if I'm looking at the mean and I compare the mean of my sample to the mean of my population and they're very different, that would be the standard error. And when we say the difference, that would be subtraction of the two. And the caveat here is they do have to be randomly selected. The sample size and standard deviation are two key elements for looking at the standard error of the mean. Any statistics that's calculated using this information can have an error. So that means if I'm finding the mean of a group, a correlation coefficient, if I'm looking at three groups of people with three different means, there can be an error anywhere in there. The standard error is usually used most often as the denominator when I'm dealing with a formula that's for inferential statistics. So we do actually calculate this value and then we input it into other formulas to be able to use it to make informed decisions. So what does this really look like? What is this? Standard error is when samples of the same size, if I repeatedly select them. So let's say I have a population, I pick 5 people, then I pick 5 people. So I'm repeatedly selecting people here. If the means of those samples were used to form a sample distribution, we would see a normal curve. So the distribution would have a mean or an expected value in the center that should match the population mean. So imagine if I'm just sampling over and over and over again, like I'm checking my work. So I get an answer and I check my work. I get an answer and I check my work. The distribution that we graph would actually be called a standard error. The standard deviation would actually be called the standard error there. So from -1 to 1 is -1 standard error, not -1 standard deviations. So if I'm looking at measures between the average difference between the two, when samples are randomly given and are randomly selected of a same size. So I know it says given size there, but it's the same size. So if I'm taking it, I'm plotting all the values for this distribution, I should see that there should still be a stack up around the population mean, which should still be at 0. That should be the expected behavior. If that does not happen, then there's some other things to investigate as we go a little further. So what is a standard error? So a standard error is actually quantified by using the statistic, and I'm going to divide it by the standard error to get an inferential value that makes sense in terms of a study. So it is basically the standard deviation of the sampling distribution, so the checking my work for a given statistic. So essentially, it's kind of hard to think of it this way, but it is a standard deviation. So think about your standard deviation formula. You do your data value minus the mean, you square it, you add them together. So we're still doing that subtraction value here, but we're just doing the mean of the sample and the mean of the population being subtracted. So what does it measure? It measures random variation, because remember, we have to use random sampling. And it gives us a random variation that we would expect if I continue drawing samples of the same size from the population. So it's telling us how much the mean should vary. So think about variance of data points. This is variance of means if I've repeatedly checked my work. And again, it's the denominator. Now, why do I want to repeatedly check my work? Well, if we think about things like the vaccine studies that are currently going on, we don't want to just do it once and then make a decision on one time, one calculation, one study. That would be problematic. We need more highly informed information. So if we try to look at an example of this, let's imagine that we want to find the average shoe size of adult American women. Let's say I'm going to pick 100 people from the population. We're going to measure their shoe size because getting everyone is going to be entirely too difficult. So I'm going to suppose that we then repeat this process to see if our mean is right, because 100 people isn't really a huge sample when you're looking at all women in America. So maybe I do it a couple times to check my work. So this process of repeatedly checking my work and taking a sample to calculate the mean and then putting those members back to be reselected is known as sampling with displacement. So basically, after I pick my sample of 100, remember, for random sampling, everyone has to have an equal chance of being chosen. So I can't take those 100 people out of the pool. They got to stay in the pool of people to possibly be selected again. If I continue this process, imagine just constantly checking your work, pulling out sample after sample after sample, and all the random samples of the population, they're going to create their own distribution, which we just saw, which is the sampling distribution of the mean. And so if I'm looking at that sampling distribution of the mean, I should be able to get an idea for, are my values kind of stacking up around the same number, or is it looking something that is skewed? Now, one of the things as we look at our ALA, if I happen to have a data set of my population, I can actually do this sampling process totally in Excel or in another statistical software by telling it to randomly pick 100 people out of my data set. So this isn't as intensive as it sounds like it might be for a researcher. So the main focus for chapter 6 is really going to be on standard error of the mean. And some key ideas from the standard error of the mean is that, again, I can plot those sample means in a frequency graph, so how quickly they stack up around a value, and that's going to form that sample mean distribution. So it's exactly what we do with raw scores, but we're just plotting means. If I do that, the mean and standard deviation of that distribution then has a special name. So we have the mean of the distribution is called the expected value, so it's kind of like the mean of the means, if you think about it that way, because the mean of the sampling distribution should be the same as the population mean. So that's why we're expecting to see the same thing. The standard deviation, like we already said, is called the standard error of that distribution. So the standard error of that distribution of means really gives us a measure of how off or how much error we can expect to see if we continue this process. So expected value, population mean, standard error, population standard deviation when I'm looking at this. So how do I actually calculate this thing? Since it's really expensive to just keep resampling and checking your work, it's often true that we sort of do this with one single sample. So when we do this, there's some key characteristics that we need. And that means the larger the sample, the more likely it is to be representative of the population. So if I want to avoid an error in the sampling process, I want to make sure I have an adequately large sample. If the variation of the scores within that sample, not within the means, if I resample, if they're diverse, we can assume the population is the same, and that can reduce our confidence in how accurately we're presenting the values of the population. What do we use this for? Like, why is it important for me to know the standard error? The standard error of the mean is used as the denominator in a z-score. So we've been doing very basic z-scores to date. Now, as we're looking at resampling groups over and over, that actual value becomes needed to find a z-score. It's also used in our inferential statistics for a t-value, which we're going to use to calculate. Now, are we going to formally hand calculate these things? No, we're going to do them in Excel. But you need to understand the way to get there is by calculating the standard error and then being able to use it. Now, notice these formulas look different. So the formula for the standard deviation of a sample or population now looks different. I have a standard deviation divided by the square root of n. So that is an interesting conundrum there. So this is different as I'm looking at resampling populations. It's like starting off with a whole new concept. Smaller samples with a larger standard deviation are going to typically have a larger error. That would make it pretty difficult to be confident that the sample represents the population. So I can mitigate this by having large samples and having a smaller standard deviation as a result, which makes me more confident in my values. And that should make sense common sense wise. If I'm thinking about common sense, the more people that are in my sample, the more it should represent the population. So along with this idea of looking at these repeated samples, we have the idea of the central limit theorem. Now, the central limit theorem is going to have a couple of requirements. So I have to have a reasonably large sample size, which we're going to say is greater than 30. Probably not the best guideline, but that's what we're going to assume for this class. It has to be normally distributed. I'm going to assume that it is. Even if the scores of the sample are not, I'm going to assume that the mean would be distributed if I looked at the population. As we talked about in chapter 4, quite a few statistics rely on probabilities that are generated from the normal distribution, which is why I need my sampling distribution to be normal. So it's more of an assumption than a proof thing. So the normal distribution and the t-distributions are used with z-score and t-values. We use z-score values to determine the probability from last week of randomly selecting a sample with a particular mean. So that's going to be the adaptation for this week, is that I'm now looking at, instead of one statistic and one data point, I'm now looking at a sample and repeated sampling. Similarly, if I look at t-distributions and I generate a t-value so that I can do an inferential test, I need to know those probabilities. So the probabilities are not going away. They're just being looked at a little bit differently. The family of t-distributions is very similar to normal distributions. So z-scores, we know, are normal distributions. And t-values are going to be very similar, but they're used when sample sizes are small. And when they are small, the middle and higher ends are near the mean and more cases are away from it. So a t-score is a workaround, basically. When the sample size is large, so let's say like 120 or more, then the t-distribution would be virtually identical to the normal distribution. So the bigger the sample size, the closer we're going to get to that normal distribution and being able to use a z-score. Now be really careful when you're using your tables, because you have to use a t-table if you're doing a t-distribution to find probability, and you have to use a z-score table if you're doing a probability with z-scores. So how do I find this mythical t-value that's supposed to be helpful to me? So to find the t-value, I am going to have to utilize the means so that I have that information included. So let's look at the distributions of what we have here for a z-score and a t-value. So the standard deviation is just going to be replaced with the standard error in the z there. And then the standard error of the mean is going to use the population standard deviation, and it's going to be replaced by the standard error of the mean. So these are new formulas that we're going to have to activate in this section. So let's continue looking at this. If I already know that I'm calculating a z-score and a t-value, and they're going to be really similar because, the sample size is adequately large, table 6.3 makes it easier to remember the difference in finding the two values. When the population and the standard deviation is known, the normal distribution can be used. If the population standard deviation is not known, then we're going to use the t-distribution. So that's how you're going to distinguish between the two. So how does standard error relate to inferential statistics? So remember, inferential statistics are where we're trying to draw a conclusion from information. So we might want to know if there's a relationship that can be measured between two different variables. And in order to do that, we would need to use the standard error. So let's look at an example. So let's say we want to calculate a t-value here. And then I have the problem on the left. So I know that my 60 minutes a week is going to be the average. That's my mean. I know I have a random sample of 144 men. That's my n. And I've drawn from the population that there's roughly a mean of 65 minutes per week with a standard deviation of 10 minutes. So I want to know what the probability of a random sample of this size with a mean of 65 if the actual population mean is 60. So I'm going to look at that by computing a t-value. I'm going to take the mean of 65 minutes per week that's coming from the population. I'm going to subtract the mean from my sample, so 65 minus 60. And then in my denominator, I'm going to have to utilize the standard error information and take my standard deviation and divide it by the square root of the number of people in my sample. So that would be 5 over 0.83. When I do that division, I get 6.02. That's my t-value. I'm not done. I then have to go to Appendix B. I have to say I have 120 degrees of freedom roughly because I'm around 144. So I'm just identifying the closest value in that table to what I can utilize. And I want to look at this sample at the 0.001 significance level. If I had a smaller sample, generating that t-value could have been a lot bigger and the probability would have also been pretty high. So again, my sample, if I'm looking in Appendix B at 6.02, I'm virtually at 0. It's highly improbable, which should make sense because here's 65, here's 60. If I'm going to be greater than 65, it's a really small probability. So let's look at another example. I have data collected from a study that is examining and comparing the beliefs of 137 students with 536 middle school students. So I've got two different populations happening here. Let's just say I want to know the standard error. So remember, standard error has to happen with repeated work where we're checking our work. So if I look in table 6.4, I've got the things that I need. I've got the standard deviation for the elementary and the middle school sample, and then I have the sample size for both. I'm going to need that in order to do my calculations. So I'm going to go into table 6.4, and the standard deviations look similar to our distribution. However, there's a large difference in the two sample sizes. So that should be something you notice right off the bat. Like you got something in 100 and something in the 500s. That's a huge disparity in the sample size. So if I'm looking at that sample size and I wanted to calculate things, I'm going to find the standard error by taking my 1.38 value. Where does 1.38 come from? It's my standard deviation. And I'm going to divide that standard deviation by my n, my number of people. And so for the elementary sample, that puts us at 0.12. I'm going to use the exact same thing for middle school and take the standard deviation divided by the square root of my sample size, and I get 0.06. So I notice the standard error of the middle school is half the size of the elementary school, because I have 0.06 compared to 0.12. So it's essentially doubling there. The difference is probably due to sample size, because I have a really large sample and a really small sample. So when I see that thing that I'm going to look at and say, something doesn't look right, that's the caveat, is our sample size is going to make things be closer to our normal distribution. So in summary, the standard error is a statistic used in inferential statistics. There's a standard error for just about every sample statistic. It's going to tell us how can we expect the sample to differ from the population. And without these, we would just have really generalized results, and we wouldn't be able to see if there's any statistic difference that's significant between means of multiple groups as I'm checking my work.